and gentlemen, and welcome. My name is Steve Bull. I'm one of the senior tutors in the Department of Electrical Electronic Engineering. I'd like to welcome you on behalf of the University, the Faculty of Engineering and our department to this evening's lecture, the Marc Grenville-Cleave Memorial Lecture. So this is the first time that we've held this lecture. Marc was a second-year student in our department who sadly lost his life earlier this year, and we've established the lecture series in his memory. Before we continue, I introduce tonight's guest speaker. I recognise we have got a lot of guests here this evening who might not have been in this room before, so just need a bit of housekeeping information. If the fire alarm does sound, we're not expecting any tests, so we will need to evacuate the building. Exits both sides at the front or at the rear of the building, and then gather outside away from the building. And the other housekeeping announcement is that this lecture is being recorded. We have a lot of other guests and friends of Marc over in the US who will be watching the live stream of the lecture this evening. So as long as you're aware of those bits of information, without further ado, I'd like to introduce Robert Smith. Robert works for a company, Rigetti Computing in the US, which he's going to tell you a lot more about as he goes through the lecture this evening, which is entitled How to Program a Quantum Computer. Robert, thank you.
Can everybody hear me in the back? Good? Great. So thanks everybody for coming down. I'm really happy to be here. I apologize a little bit for my jet lag and also that I have this big stack of crib notes that I want to follow, but I want to make sure I get through the points and get them done on time. So I work as Director of Software Engineering at Rigetti Computing. We're a company that builds quantum computers and deploys them. They're actual real devices, which you'll see soon. I work mostly on of course, the software aspects of this. I'd like to talk a little bit about how we might think about programming a quantum computer, sort of from first principles. Before I begin, I would like to talk about my friend, Marc Cleave. I'd like to introduce you to him. The namesake of this lecture is named after him, of course. In my career, I've had a chance to meet lots and lots of people. I do lots and lots of interviewing, lots and lots of speaking to people from other companies. And it goes without saying that Marc was truly on another plane. You meet all these people who get double majors, triple majors. They've accomplished many different things, maybe published papers before they even got out of school. But to me, Marc was a sort of like millennial Steve Wozniak. He had a penchant for good quality, sort of grounded engineering, and he really knew how to do engineering from first principles. This is, of course, a picture of him typing on his laptop. He's also super into old computers. I would not be surprised if many of you don't recognize every single machine there. I had the opportunity of knowing Marc for about a quarter of his life. In the pursuit of finding like-minded individuals, perhaps many of you are like this as well, we met online, met in different channels for actually old computers, and then we found that many of our interests were very similar, and we started to talk about other aspects like programming and what have you. I think my first recorded correspondence with him was back in 2012, and really the correspondence grew since then, almost to speaking nearly daily online. I did have the opportunity to meet him in person back in 2013 when he came out to California, and we actually visited places like the Computer History Museum down in Mountain View, California. I would say a major theme of our discussions was my mentorship of him. I mentored him mostly in the areas which I'm well trained, which is software, especially kind of the brass tacks of software like just fundamental computing, computer science, programming language theory, and the like. And what I felt is that when we spoke, I gave him a sort of opportunity to understand the engineering that he did in a sort of more fundamental fashion. The engineering that he understood very well, he didn't understand that there are sort of mathematical principles behind them. There are ways of formally reasoning about the things that you're building. So while it's fun and interesting and quite a lot of joy in especially electrical engineering to actually like wire things together, there are lots of things that you can determine, debug, and figure out about a system simply by reasoning about it formally. With that said, I don't want to give this impression that Marc was this like die-hard academic. He was an extremely entertaining person. He had a very curmudgeonly humor. And really, it was very difficult to even sort of determine a time when he was ever super serious. But you could tell he was serious about his craft by the sheer number of accomplishments that he's made. So here's a picture of Marc. That is not a gun. That is something that is called a wire wrapper. It is used, you can see it in the top image up there, these little coiled wires. Marc had built his own CPU from scratch back when he was a teenager, and then built all the tooling on top of it. Building a CPU or designing a CPU or learning about the fundamentals of a CPU is something that you might do a few years into a university course, let alone building one from scratch when you're a teenager, when you don't know how to program, proceeding to learn how to program, to build an assembler for your CPU, proceeding to build a compiler for a language that targets your assembler, and building the whole tool chain on top of that, I think is really a work of genius. It's something that I certainly couldn't have done, and none of my colleagues that I know could have done. It has been a really, really impressive feat. So this board right here is one of the boards. It's actually a clip from a YouTube video, which you can see where he explains it with total competency, explaining how the CPU that he built actually functions. In my opinion, before he even entered university, he really had all of the knowledge to claim a degree in computer engineering. I don't want to underestimate the feats that he's gone through. A little bit more about the software. This is actually a little snippet of code from his software. I don't know if people can read it, but it's very serious but playful at the same time. So it's hard to recognize, but this assembler actually has a structure of something called a nanopass compiler, which is something that came out, a relatively recent idea that came out within the past 15 years, I think, at the University of Indiana. And it's a way of structuring your compiler in such a way that it's very, very easy to understand. It's very compartmentalized and very modular. But in there, you can see all these fun comments. The top comment up there says, slightly less dirty could almost be considered clean. And in the middle of it, it just has things like black magic, but then the comments proceed to say, like, substitutes things built up in the environment, substitutes registers for values, et cetera, et cetera. This isn't a functional programming language. He coded it in a functional subset of the scheme programming language and used, by and large, immutable data structures. Even to lots of expert software engineers that I work with, this in and of itself is like a difficult thing to come by. And I find it especially difficult for individuals who think in terms of machines, think in terms of mechanisms that have state. Marc was also the kind of person who was a little bit against the establishment. He was a little bit nonconformist, and so I feel that I have to prioritize that a little bit. I realize I'm in a university, but I have to do something that Marc would do, which is get a little shot of gin and do it in the middle of my talk. Gin was, of course, Marc's favorite drink, and we've had many good times drinking and studying together. As a final picture of Marc, this is him working on yet another old computer, and it seemed to be a theme. He seemed to have an appreciation for the lessons that one could learn in technology that was very well engineered and very old. It's my profound honor to be able to speak at this first lecture in his memory. And without further ado, I'd like to continue talking about something which he loves a lot, which are computers. So computers are devices that compute. Back in the day, computers didn't actually refer to any sort of electronic machine. They refer to people doing arithmetic on paper. The picture above is one of a bunch of human computers at NASA doing computations for anything that we're doing, especially back in the 60s. If you saw the recent movie, that kind of gives you a little bit of view into what it was like prior to the adoption of large computing machines. The development of computers, however, sort of dovetailed along with the development of the formal notion of computation. Almost philosophically, many people, including these two individuals, thought about what a computation is. These individuals are Alonzo Church and Alan Turing. Interestingly, Church was Turing's thesis advisor, yet they had very, very different ways of thinking about what computation is. So Alonzo Church thought about computation with a sort of mathematical edge to it. He thought about computation expressed in terms of these mathematical formulas called lambda terms to create a computational study called the Lambda Calculus. The notion of computation itself was encoded in how these terms simplify. It's a very rough analogy, and for experts in the crowd, I'm going to be making lots of rough analogies in this talk. As a very rough analogy, you can think of computation as doing the equivalent of simplification of an expression. It's not quite true because the expressions in the Lambda Calculus sometimes expand, become greater, sometimes don't even terminate in their simplification. But nonetheless, the feeling of a computation was writing down a mathematical formula and manipulating it in a very formal sense. Turing did a completely different idea. He thought of computation as something to be executed by a machine. This is a little cartoon drawing of something that has become known as the Turing machine, which is dedicated in his name. The Turing machine is a machine that encapsulates this idea of an abstract machine. You'd never actually build a Turing machine. It's just useful to think about. It's useful to prove certain theorems or facts about computation, but it's not something you'd actually construct. Nonetheless, it really brought forth this essence of thinking about computation as work done by a machine. A lot of this talk I actually want to dedicate to talking about the notion of an abstract machine. To me personally, the study and thinking of abstract machines is what allows me personally to even broach the subject of quantum computation. So before getting into that, I do want to spend a good amount of time on abstract machines. So Fineman, Richard Fineman was a very, very great lecturer. He was a very, very great physicist. I would not be surprised if nearly everybody has heard of him. Very charismatic, and he himself was a genius. Sort of in his later years, he got really interested in computation as well. There's a really nice series of lectures on YouTube, actually, of Richard Fineman talking about what a computer is and how it works, and I highly recommend it. He describes a computer as a really, really dumb clerk who kind of runs around somewhat comically, shuffling in and out of like filing cabinets, putting papers in, taking them out, going to a filing cabinet, taking paper out, doing like one simple little addition, putting the paper back in, et cetera, where the clerk was an analogy for the central processing unit of a computer. The filing cabinets were analogies for the memory of the computer. And the instructions written on the card, the things that he had to do, were analogies for the program. In Feynman's words, as you see up there, he said, "The inside of a computer is dumb as hell, but it goes like mad." And this is really a sort of central point to how computers work. They do very, very simple tasks, but at very, very quick, fast speeds. Like I said, I highly recommend looking into his lectures. I think that they're entertaining, but also quite informative. However, I don't think that his description of a computer brings about what I consider to be very, very important, which is this notion of an abstract machine. And generally, when you're trying to look for a common abstraction, you look at a bunch of examples and see what's common among them. So I'd like to talk about two of them in particular. So this machine is a computer from the 60s, the Honeywell H316. It's a machine that has, I think, 32 kilobytes of memory, and it runs at something like a billion times slower than modern machines. In particular, it runs a billion times fewer instructions per second as like a modern Intel processor, for instance. What's interesting about this computer is that one of the modes of entry of instructions into the machine is actually through paper tape, and you can see it right there. These punched holes in the tape. What you would do is you'd turn on the computer, load this tape in, and it'd reel it in, and provided it didn't jam or the tape didn't tear or anything like that, your program would be loaded into memory. After you do that multiple times, because your program would be set across multiple tapes, they would be linked together, as they say, and then you literally would hit a button on the machine to run the program. There's no screen that, so to speak, for this machine. What you actually usually did is hooked it up to a printer that actually printed out ink almost like a typewriter and printed out the results that way. The main point to me of this is that the medium of entry of instructions is through this paper tape. Another example of a machine is one that Marc actually had, being a collector himself, which is the PDP-11. The PDP-11 is a machine that actually came in many varieties, is a very popular machine sold by DEC over several decades, actually. This one in particular, or many of them, I think one of the best in the class was one that I think had 4 megabytes of memory. And ran at a faster speed. But what's most interesting to me is that this is one of the first machines that ran a true Unix operating system. This is one of the first machines where programming these machines is very similar to how we think about programming machines today, like my laptop or this machine over here. You go into the operating system with a keyboard. On these machines, generally, you hooked up to some sort of teletype terminal. Typed in, they have the classic green screens usually. Worked on your program, compiled it within the operating system, and ran it. This is actually a shot from one of a little bit of a test fixture where something is being tested running on the PDP-11. In this case, the program was written in straight assembly, so the program could be run directly. Saying what to do to a computer, I think, is a very important subject and a very important thing to kind of wrap your head around. What to do is sort of a verb, it's an action, you're doing something, and that sort of necessitates the idea of a noun, an object, something you're acting on. In this notion that you have an instruction acting on something, a noun and a verb, to me, kind of encapsulates the idea of an abstract machine. You have some sort of state, and then you have some notion of transitioning that state, somehow changing it in some way. So we can think of an abstract machine as state here, and then instructions, that this machine somehow executing these instructions so as to change the state. We're not specifying the mechanism of how these instructions are put in, how they're loaded, how they're encoded, or anything like that, except that fundamentally the machine has state in a way to change the state in a well-defined way. What I want to do is try to construct an example of an abstract machine that's relatively simple, kind of brain-dead easy, and sort of go through that. So one type of machine might be just a machine that counts. Here, the case, we would have state, which is just a number. This machine all has is a number. You might think of this machine as like one of those old mechanical clickers, where every time you click the button, the number would increase. Here we're saying that there are 2 instructions, one instruction to increase the number by 1 and one instruction to decrease the number by 1. Our nouns our verbs are to increase and decrease, and our noun is that number being incremented and decremented. When we have these verbs, we can chain them together into a sequence of instructions to construct programs. So one program, again, maybe not very useful, is a program that says to increase, decrease, and increase. And provided that our state starts at 0 and we run this program, we're going to get some effect afterwards. So we execute the increase instruction, we're going to get to 1. Execute increase again, we get to 2. When we hit the decrease instruction, we go back to 1. And when we increase, we get to 2. So the final state, provided the definition of this machine is that it halts afterwards, is that we're left with a state of 2. This isn't a terribly useful machine, given that it just counts up and down. Maybe it's good for, like I said, building a little clicker if you just wanted to count how often something happens. But we can immediately get something much more interesting by introducing this idea of a program counter. So a program counter is an additional piece of state that just says, where are we in this program? When we run the program again, we see that, well, we executed the first instruction and we've gone 1 instruction in. We've executed another instruction and we've gone 1 in. The number is not changing, and it should be changing, kind of like in the last slides. But the main point is that the program counter itself is increasing as we go up and down through instructions. So what might be interesting is to add an instruction that itself takes into account this program counter state as a part of the computation itself. If the program counter state is dictating where we are in the program, then it might be nice to effect where we are in the program. So we might add another instruction, jump when positive, which says that if our number itself is positive, then we want to jump forward or backward a certain number of instructions dictated by this number n. So we can construct an interesting program. Maybe we do a decrease instruction first, and then jump when positive in -1, so we jump back an instruction. You should take a moment to think about what this program might do if we were to run it. So if we run it, let's suppose we started our initial state was with the number 3. Our program counter starts at 0. We would hit the decrease instruction. Our number goes to 2 and our program counter goes to 1, of course. Jump when positive, well, we see that our number is still positive, so we're going to jump back an instruction. We decrease again, the program counter becomes 1, and the number is 1 because we've decreased again. Go ahead, it's still positive, so we jump back. Our number is 0 again, and now we notice that our number is no longer positive, it's 0. So our state ends with our program counter being 0 and our number being 0. In effect, we've created another program which resets the counter, the number of the program. To me, this is a very, very powerful concept that we've taken a few basic primitives and we've created something called an abstraction. We've created a subroutine which now acts as a sort of black box. We might call this subroutine reset. So every time we call this sort of pseudo instruction called reset, what's actually going to happen is that our program counter is going to decrease back to 0. The notion of abstraction is a concept that's pretty well understood, taught in a lot of computer science books. For instance, Structure and Interpretation of Computer Programs, I think the entire book is dedicated to the idea of abstraction. Abstraction is what allows a programmer to start reasoning about things kind of at his or her level. For instance, this slideshow software, the programmer writing this software isn't thinking about incrementing or decrementing numbers or anything like that. They're thinking about slides and presentations and text and the like. And that's only a possibility with the idea of abstraction. So to recap, an abstract machine is something that has nouns and verbs. These verbs affect these nouns in various ways in the form of state and state transitions. Because I promised that I would talk about how a quantum computer works, I do feel necessary to delve into physics just a little bit. But as we'll see, there's actually a lot of similarities between what we've spoken about so far and the physics that we will discuss. So there are lots and lots of fields of physics. You can't encapsulate them all in even a single slide. But as it pertains to the motion of bodies and the like, I would broadly categorize there to be sort of three main fields of physics. There's the physics of how stars in the universe move and work, and how gravity works, and how things over extraordinarily large distances are affected over time. This is what I sort of call the physics of the large, and formally this is called general relativity. Then there's the sort of physics of the ordinary. There's the laws that govern how billiard balls move, how cars work, how just about anything that's sort of life-size, quote-unquote, operates. And this is called classical mechanics, or Newtonian mechanics, as a particular type of classical mechanics. Then there's also the physics of the small. These are like really, really small items, like subatomic particles, molecules, and atoms. They are not governed by the same laws of physics that we sort of see day to day in our lives. Really weird sort of types of physics. And this is called quantum mechanics. I want to discuss, start a little bit about classical mechanics, and then get into quantum mechanics a bit, which we'll need to understand how the quantum computer operates. So classical mechanics has a long and rich history. I'm not going to go through everything about it, but one of the main takeaways from my studying of classical mechanics is that you can actually really think about the world itself as a large machine. Using the laws of classical mechanics, you can reason about the world as if there was a bunch of state. I might think about, for instance, this bottle of water right here as a bunch of little point masses. Each of these little points themselves move through space in different ways. And if we were to somehow characterize what each and every little mass did, then we understand the mechanics of the bottle itself. Now, in classical mechanics, it's well known that if you know the positions of everything and the velocities of everything at any instant in time, for instance, this bottle of water is roughly standing still, its position is right here on the table, and its velocity is 0, it's not moving at all, then we can predict that this bottle is not going to move. It's a little bit sad in that sense, because if you know the initial state of something, then you know its entire future and past. But fortunately, at least the way I think about it is humans have free will, so we can arrange our reality in such a way that we can take advantage of the laws of classical mechanics to do useful work, and in fact build computing machines. So we see here that, as I said, that we can think of classical mechanics as indeed an abstract machine itself. Kind of using the diagrams that I showed earlier, our state, our nouns, so to speak, are the positions and velocities of a bunch of little masses. Again, if we were to divide this bottle up into a bunch of little pieces, and we recorded every single position of each little piece, which I've denoted here by P1, P2, et cetera, and we denote every velocity of each piece by V1, V2, et cetera, then we can run this machine by running it through Newtonian mechanics, in particular, Newton's equations. Like I said, we can take advantage of the way in which classical mechanics works to do useful computations. We can take this abstract machine right here and apply it to reality to do a useful computation. And one of the greatest examples was this mechanical computer invented by Charles Babbage. I think he was at Oxford, I believe, when he started working on it. This itself was not built by him. This was commissioned to be built by Nathan Myhrvold, and it has been sitting housed at the Computer History Museum for quite some time. This machine is one that is purely mechanical. It's used to evaluate these mathematical objects called polynomials. Doesn't really matter what they are, except that to say that it does useful arithmetic, useful and complicated arithmetic that takes very long to do by hand. To me, this is a demonstration of using the laws of classical mechanics, with lots of layers of abstraction, of course, to ultimately use reality and the way reality works to do a useful computation. It's one particular embodiment of this abstract machine. This idea that physics or lots of fields of physics can be thought of as state machines that can be used to do computation is how we get to the idea that quantum mechanics can also be used to do computation. So, as I said, quantum mechanics is the physics that governs how small particles behave. Quantum mechanics allows us to predict how electrons move, how protons and neutrons work. It's not strictly a science of how things move, because the notion of movement at very, very small scales is actually a little bit counterintuitive. Richard Feynman, like I said, was a physicist. He was also a quantum mechanic. He primarily did quantum physics. He opened up all new fields of quantum physics and lots of discoveries in the theory of particles and so on. And he actually supposed in the 1980s that quantum mechanics could be used to do some sort of useful computation, that we could make sense of the laws of quantum mechanics in order to compute something which would otherwise be very difficult to compute. As you all might imagine, I can't make the rest of this lecture one about all of the details of quantum mechanics. I can't, reteach linear algebra and differential equations and all of that. But there is one point, one very, very salient point, which I think is pretty easy to drive home, which is that quantum mechanics is inherently difficult to calculate with. It's inherently difficult to simulate. Computers do a great deal of work simulating all sorts of things. We can simulate how good an airplane works. We can simulate the weather. We can simulate, even modern video games are turning more and more into elaborate physics engines. We can do all those simulations with relative ease. We can just put more resources and do it. Quantum mechanics, however, is not so. Quantum mechanics is a lot more difficult. And the main reason is because when you have a bunch of small particles, they all can interact. And keeping track of how all those interactions work is very, very consuming. And I'd like to try to illustrate that. So one property in quantum mechanics is that a particle, in this case it's a photon, but it doesn't matter, can oscillate. It can move in one of two different directions. Here on the left side, you see this particle sort of moving left and right. It's sort of oscillating back and forth. And on the right-hand side, you see the particle can also be moving up and down. The particle only moves left and right or up and down. There's no side to side or diagonal or anything. There are only these two possibilities, left and right or up and down. But perhaps if we don't look at it, there's a probability, maybe 50% chance that it's moving left and right or 50% chance that it's moving up and down. We say that the particle is in one of those states or is in a combination or so-called superposition of both of them. This is where you get all the sort of nuttiness about Schrodinger's cat being dead and alive at the same time and so on. It's no different here, that the particle is either moving left and right or up and down or some probability in between. We could imagine kind of duplicating this picture twice, and we can think of two particles. But some funny business happens when we start considering that if we don't know if the particles are moving left and right or up and down, and we want to write down all the possibilities, all the probabilities that the first particle is moving left and right and the second particle is moving left and right, or the first particle is moving left and right and the second one is moving up and down. When we write it all out, we get this table. So in this example, I'm saying that there's an 80% chance that our first particle is moving left and right, and the second particle is also moving left and right. There's a 5% chance that the first particle is moving up and down, and the second particle is also moving up and down. And so on and so forth. You can kind of write out every possibility. Now if we were to imagine what it might be like for three particles, how many numbers do we have to write down to really fully elaborate on all of the possibilities and all the probabilities of all the possibilities? It might be tempting to think it's 6, just add another 2 rows, but actually we double. Because we have to consider every single possibility, all three particles moving left and right, the first two particles moving left and right, just the first particle moving left and right, all of the particles moving up and down, maybe the first two particles moving up and down. You can see in these columns, every single possibility is there, and each one is associated with a probability. So now you might imagine adding a fourth particle. What does this mean? It means that the size of this table itself will double again. So if I'm interested in trying to use a computer to study quantum mechanics, and I want to think about 100 particles maybe, there are just way too many. In fact, here, if I have, on the left-hand side, I have the number of particles that I want to study or simulate, and on the right-hand side, I have the number of probabilities that I have to keep track of. You see that while the left-hand side is only growing by 10 each time, the right-hand side is growing way, way, way too fast. That third number for 100 particles, you'd have to keep track of 1 nonillion probabilities. Like I don't even remember. I had to look the name of that number up. It didn't. I don't know it off the top of my head. For 1,000 particles, you'd have to model this with 1 followed by 300 zeros. Now, it may just seem like, oh, well, maybe we should just get bigger and bigger computers. If we just got a big computer to just hold all these numbers together, that we could just do the computation. The problem is if you tried to take every single atom in the universe and dedicate that to building one giant computer, you actually would just run out of atoms. There are not enough atoms in the universe to encode a computer that can hold something that could simulate 100 particles with perfect precision. So it suffices to say that quantum mechanics is a very difficult thing for ordinary electronic computers to simulate. Feynman also thought of this, being a smart guy, and he said, well, if we're not going to use an electronic computer to simulate quantum mechanics, let's use quantum mechanics to simulate quantum mechanics. Let's think about quantum mechanics itself as an abstract machine that if we could build in some way, using the state of quantum mechanics and the state transitions that come together with quantum mechanics, if we could build a computer, then we could tackle these problems. We wouldn't need to store every single probability because it'd be inherently encoded in the quantum mechanics itself. He took the first step. He was motivated mostly by what I might say chemical interactions and the like. He created these objects which he referred to as lattice works, where he had a bunch of atoms kind of arranged into a lattice, and you could sort of do these pairwise interactions. However, Feynman didn't really deeply broach the technical subject in this way that Church and Turing did of classical computation. They didn't really Feynman didn't really discover what new computation you could do, how it was, and so on. He didn't give us a formal theory for understanding this stuff. It was nonetheless a good idea. So what I want to start getting into is how we can start thinking about a quantum computer using these ideas of an abstract machine. So after Feynman, there was somebody, David Deutsch, who did think about this stuff. He thought about the question, what is a quantum computation? In the same way that Church and Turing thought about what is a computation. He's at the University of Oxford. He did his study, he did his work and published a paper back at the University of Oxford in the 80s. And following suit with Turing, he attempted to create a machine that simulated quantum mechanics to do quantum computations. This is a direct quote from his paper. He said, like a Turing machine, a model quantum computer consists of two components, a finite processor on infinite memory, of which only a finite portion is ever used. The computation proceeds in steps of fixed duration, and during each step, only the processor and a finite part of memory interact, the rest of the memory remaining static. To me, this description doesn't read like anything you'd read out of a normal quantum computing textbook. This reads like a machine that executes steps with a certain number of resources. It doesn't say exactly what the steps are here in this little excerpt or exactly what the machine looks like, but you can see that we're sort of getting a mechanical description of something. While I think Feynman gets a lot of credit for thinking about quantum computation, I really think that, that it was Deutsch who really opened the field of quantum computation. And so, in fact, I really think the UK here, which I'm happy to be in, is actually the birthplace of real quantum computation. And in fact, Deutsch's paper led to the quantum Turing machine, which is sort of 2 for 2 for the UK in defining computation in general. So the quantum Turing machine is what comes out of Deutsch's paper, which is an analog to the Turing machine, but expands its computational abilities in various ways. He defined this in formality. Again, it's just like the Turing machine. It's not useful here to talk about it, but we can get to the essence of what this machine might look like. So now I have to abstract away from some of the things I talked about and define a qubit. So a qubit is, as it sounds, is like a quantum bit. But really, the way to think about it is that when you have something that can be in 2 states, or possibly in one state or the other with a certain probability, then you can think of it as a qubit. Yes, I am speaking again very roughly here. The correct definition of qubit is like a 2-level system in this complex finite dimensional Hilbert space and blah, blah, blah. But more or less, a fine way to think about it is something that can be, like, for example, this photon going left and right or up and down. So a qubit is an abstraction of the possible nouns in quantum computation. There can be other types of qubits. For instance, superconducting charge qubits, as they're called. It's a really crazy name, but in the end, it follows the same abstraction of having 2 states and a possibility of being in either or. So in this case, superconducting charge qubit is actually a little bit more concrete than this photon business. You can see up there, there's a chip. Actually, each of those large squares in the chip is a collection of 8 qubits. 8 superconducting charge qubits. You can barely see it. There are tiny, tiny little squares in those things, 8 of them, and each of those itself is a qubit. So the main point is that these little circuits either have a charge or they don't have a charge, or they possibly do with a certain probability. And that makes them perfectly viable qubits. But what's more interesting is that they're made out of silicon, using the same, more or less the same manufacturing techniques that we use to build any other kind of chip. It's amazing that, to me, that a quantum computer is something that you can just hold in the palm of your hand. So like I said, it's not important to get into all the details of how they work, but I do want to talk about kind of a little bit more context around superconducting charge qubits. So this chip that you have right here, you house in one of these white refrigerators that you see in the background. The reason for this is that they have to superconduct. And in order to superconduct, they have to be very, very cold. Superconducting means that electricity flows through it without resistance. I don't know if you guys have ever put a wire on a battery or shorted the terminal, but it heats up. It heats up because the wire is resisting. There's resistance, and that turns into heat. However, when you cool some metals down very, very, very cold, all of the resistance, everything disappears. So electricity flows without turning into heat or anything like that. So these dilution refrigerators, they look fancy, but I learned that you can actually just buy them. If you have, I don't know, a couple $100,000 to spare, you can get one installed in your own home. So you put those chips, again, this tiny chip, one of those little squares, into this big machine, and you can see sort of on the side where this bottom arrow is pointing that there's a whole rack of electronics that are a bunch of these coaxes that are going into the machine. These coax cables are how you interact with the machine. It turns out that these circuits are not electrical circuits. They're circuits that use microwaves. They're the same types of circuits that you'd find in an antenna or a radio or even Wi-Fi. Anytime you have electromagnetic radiation, anytime you have a radio, basically, you're going to have some sort of radio circuit. So indeed, this circuit is not an electrical one, it's a radio circuit. So how do you interact with radio circuits? Well, the same way you interact with any other radio circuit, which is you send waves into it. So here's another picture of the chip. The chip is just the tiny thing in the middle, and it's housed in this thing we call a puck. It's a mechanical fixture that allows you to load it into the dilution refrigerator. And these lines, these little circles on the outset, allow us to contact and send microwaves into it. So how we interact with this machine is we generate a microwave pulse, radio pulse. and we fire it in, and it travels into the chip, and it just affects it in some way. Again, it's like a state machine. The internals of this machine are the state of the qubits, and the pulse does something. So in that sense, we can start thinking about two new verbs. We can think about the verb to transmit and to receive. However, those aren't quite the right verbs. It's like saying that the verb for to go turn off a light, for instance. It doesn't make sense that the verb for that action is to like depress your finger on a light switch. It's to turn off the lights. The verb is to turn off the lights, and the state is whether the light is off or on. The verb is not to apply force with your finger to a light switch. And so in the same sense, the verb here really isn't, while we are sending, while I do press a light switch with my finger, or while I do send microwaves into this machine, that's not the real operative verb that we should consider for understanding this abstract machine. So one of the simple operations that we can consider is measuring a qubit. This is a really simple thing. I said that qubits are things that can be in one state or another, or possibly one or the other. At some point, when you actually look at the qubit, when you look at it or measure it using a measuring device, you can actually see if it's one or the other. For instance, with these superconducting charge qubits, you can actually measure, does it have a charge or does it not? In the end, you'll get that measurement, and measurement itself is a verb in this system. So how do you do a measurement with a superconducting charge qubit? Well, you fire a pulse in, and basically you listen to see if anything gets reflected back. So you'd think of attaching all these instruments. One line itself is sending, this other line is receiving. I send a pulse in, and then I wait on the line for receiving. If I receive something, then that means there's a charge. If I didn't receive anything, then that means there's no charge. And we know with 100% certainty whether it has a charge or not. It turns out we can think of measurement itself as like an instruction. We can think of it as a proper verb in the system. Here, the instruction is measure a qubit and put the answer into some classical memory somewhere. Maybe we have a box or something like that that says, does it have a charge or does it not? So our instruction here, our verb is to measure, and our nouns here are the qubit and the classical bit, or the classical memory where we store the answer. So measurement is extraordinarily important to a quantum computer. It lets us like determine any sort of answer at all, because at some point we have to like look at what's there. It's important in Cornerstone, but it doesn't exactly tell us how to like do anything with the quantum computer. Like, yes, we can read its state in and out, but we haven't insofar discussed how we do something. Fortunately, we have all the tools necessary to discuss the things that we can do with a quantum computer. And so one of my absolute favorite things is to look at the qubit as a set of probabilities, and as such, I can think of it as flipping a coin. So sometimes when I want to make a decision, like if I can't decide, like if I want, I don't know, tea or coffee or whatever, I'll spin up all these like millions of dollars of hardware to simulate a coin flip on a quantum computer. I mean, it's all about probabilities, so it seems like a reasonable application to me. So here, what I think is that I take a qubit, and if it has a charge, I say that's heads. If it doesn't have a charge, that means it's tails. So what I want to do is try to construct a program to do this. Like I said, qubits just encode probabilities. And a new concept, a gate application, is what allows us to change these probabilities in a favorable fashion for us. So when you power on one of these quantum computers, everything starts off as normal. The charge, there's no charge there to begin with. So you know with 100% certainty, as you can see in this table down here, that the qubit of interest is always in the tails position, and there's a 0% chance that it has heads. So it's not a very useful coin flipper yet. So what I want to do is find some gate application, as they're called. The operations on a quantum computer are called gates. We want to find some gate application that will bring us to a table like this one over here, where we have a 50% chance of tails and 50% chance of heads, if we want to make a truly fair coin. So gate application is what we think of as the operations of a quantum computer. Some of you might be wondering, though, that like, since we're sending in these microwaves, there could just be an infinite number of them. I mean, we could construct any such wave that we wanted to. I mean, even listening on the radio, you've probably never heard the same thing on the radio twice. It's always different. So there are all these enormous number of possibilities. And that sort of collides with this idea of having fixed, discrete instructions for the machine. We don't want to be sending these analog pulses. We want to think of the machine as a digital, discrete machine whose state changes upon discrete instructions. Fortunately, some people did math, and we learned that there are 4 gates that can encode any possible quantum computation. Unfortunately, the same people who discovered it also are terrible at choosing names. So we have these 4 really obscure sounding things: H, phase, T, and C naught. The first 3, H, phase, and T, are 1-qubit gates. They are pulses that you can fire on a single qubit to change the probabilities in a favorable and well-defined way. C naught is something where you fire 2 pulses simultaneously on neighboring qubits, and it changes their correlated probabilities in a particular way. It turns out that if you do these things in the right order, you can simulate any other possible gate at all that is possible on a quantum computer. So this H gate has another name. It's called the Hadamard gate, if you want a keyword to look up on Wikipedia. And the Hadamard gate is indeed the thing that we're going to be looking for. So since gate application is another verb in the system, and we know that firing pulses changes the state of the system in some way, then we might as well create 4 new instructions for a machine. We can say Hadamard on a particular qubit Q. We can say phase on a particular qubit Q, the T gate on a particular qubit Q, and then C naught, which is a 2-qubit gate, as it's called, on 2 qubits P and Q. And so when we go back, we had this picture originally. I just said there's some gate application that'll do that. Indeed, the Hadamard gate will take us from something where we know with 100% probability that it's tails. If we have fired those pulses, then we actually don't know anymore. It's going to be 50% chance of being heads or 50% chance of being tails. So now we can actually write a quantum program as something that is of dubious use, but is nonetheless useful to me. Here, the quantum program is apply Hadamard on a particular qubit. Here, like I said, our chips have 8 qubits, or some of our chips have 8 qubits. We just number the qubits, 0 to 7. So we can say, fire a pulse on qubit 2, fire a pulse on qubit 5. In this case, we're saying, fire the Hadamard pulse on qubit 4, which is going to bring us into a 50% heads, 50% tails situation. Then we want to measure qubit 4, but we need to put the answer somewhere. And we designate the boxes in which we can put answers by this other number here. In this case, we're going to say, put the answer into 13, into register 13. So after I run this program, when I look into register 13, it's either going to have a 0 in it or a 1 in it. And I get my answer, 0 being tails and 1 being heads. This is actually a real quantum program. This is not pseudocode right here. This is something that you can actually readily execute today on a quantum computer. I want to bring back this mantra of abstraction, which is also exists in the context of quantum computation. So maybe coin flipping is a useful thing. Maybe I want to use it a lot in my program. Maybe I want to flip 5 coins or something like that. Here we can actually define a subroutine for this, saying called flip coin, where as long as we provide a qubit and a place to put the answer, we can say do Hadamard on that qubit and measure on it. And so henceforth, instead of having to write out this program with these special numbers and everything, we can actually just say flip coin, 4 and 13. So I want to drive the point home that thinking about a quantum computer as an abstract machine, something that has state in a particular collection of verbs to change that state, to me has been a very fruitful way of thinking about how to actually write programs for a quantum computer. To recap, here an n-qubit quantum abstract machine is something that has n qubits. That means we're going to have 2 to the power of n probabilities if you've been following along. And then we're going to have a place to deposit the answers from measurements, and we can have as many as we want, maybe thousands. Our instructions here are measuring, and then these 4 other gates, H, phase, T, and C naught. And with those 4, those really form a sort of assembly language for a quantum computer. So I talked about this sort of in the abstract, being abstract machines, but like I said, these are real programs and things that you can actually run. So if you're interested in actually all of the nitty-gritty details and actually the abstract machine model of a quantum computer, there's a nice paper, it's nice because I wrote it, called A Practical Quantum Instruction Set Architecture, which talks about the abstract machine architecture of a quantum computer with all these other frills and niceties that you get, like being able to reset all the qubits to 0, for instance, and actually being able to have that control flow that we did earlier where you can sort of jump around in your program. It defines it nice and formally. So on the left-hand side is for people who feel like they're mathematicians or maybe computer engineers who like that, but then the right-hand side is like people who just want to try stuff, who don't really care about all the little details. And so something that we've built at Rigetti Computing is a little library in Python that allows you to construct these quill programs. So this is actually, like I said, valid quill. And PyQuil, you can construct these programs, but not only that, you can actually send them off to a real or virtual quantum computer. You have to get an API key, which you can sign up for on Rigetti's website. But it allows you to access the real quantum computers and the virtual quantum computers if you sign up. To me, it has been very, very interesting to be able to actually code on a quantum computer. My background is not physics at all. I barely know anything about physics. But having a view of computer science and looking at things in terms of machines in the same way that often we look at physical theories has been profoundly helpful to me to understand how to actually really program a quantum computer. I think this talk touches on lots and lots of topics that were of interest to Marc. Marc was particularly interested in old technology, new technology, but particularly of interest is how old technology informs us how we can build new technology. We've discussed how we can take really, really old ideas, like the notion of a Turing machine, or really what a Turing machine represents in the abstract sense, and apply it to something which is really bleeding edge, which is quantum computation. If Marc were here today, this is how I think I would have gotten him to grok quantum computing. If there's any topic that I've missed, I think it would be Marc's love for the Range Rover Classic. I want to say thanks to, I want to give a big list of thanks to many individuals. First and foremost, I actually want to thank Marc's family for being able to make it here from way down in southern England. It's really delightful, and it's a pleasure to be able to speak. I also want to thank Stephen, who really pushed for this to happen. I mean, to a point where he was really getting on me for getting things done and over the finish line. I also want to thank the University of Nottingham. I've been very, very pleasantly surprised with how clean and nice and beautiful the campus is. I'm also very, very happy for the university's willingness to show compassion and kindness in and towards Marc's memory. Lastly, I want to give thanks to the crew with whom Marc and I were banded together for a long time. These people are Toby Thane, Mark Skilbeck, Joey Gooley, Aaron Jackson, and Matt Young. Each of these folks were longtime friends of Marc, interacted with Marc in very diverse but nonetheless similar ways to the ways in which I've described, but really gave him an environment to exercise his intellect and wit, I believe. Without them, I don't even think this talk could have happened. That's all I got. Thanks everybody for being able to make it down here. I'll be happy to take any questions that anybody might have.
Okay, thank you very much, Robert, for a very interesting, informative talk. I think also, having known Marc, as you did also, really great in his memory. I think he would have really approved the topic and the level, and yeah, I think you've convinced him. I think you've convinced me as well. So if there are any questions, I'm sure Robert will do his best to give you an answer. Start in the middle.
So I was wondering, what's the state of the art in all the quantum computers, especially in relativities computers? Like, for example, how many entangled quantum qubits can you handle at the same time, or use for dense coding and all this?
Yeah, okay, so the question was kind of what's the state of the quantum computers today, and what possibilities do you have? So of course there are things that I'm unable to say. But what I definitely can say is that we've released and have publicly announced and have public usage of our 19-qubit chip. Our 19-qubit chip is fully connected, so you can construct entanglement across all 19 qubits. The fidelity numbers are around, for 2-qubit gates, are around the 95% region. 1-qubit gates are 98 to 99%. And so you get the issues that you get from there. And then measurement fidelity is also 95+%. So you don't get crazy long gate depths. Basically, gate depth is the length of the program that you can run. You don't get very, very long running programs that don't accumulate error over time, of course. So with that, I would say that you can sort of infer what's possible. So things like Shor's algorithm are not routinely executable on these machines. However, in the past 4 or so years, a new class of algorithms have been developed, which are called hybrid classical quantum algorithms. These are algorithms that use actually a regular electronic computer, a classical computer, and a quantum computer sort of in tandem with one another. These are typically problems that are good for optimization and the like. So one of these algorithms is the variational quantum eigensolver, for instance. The variational quantum eigensolver is an algorithm that, given some linear operator, it can actually compute the eigenvalues of it, and those are used for all sorts of things like optimization and what have you. In fact, that's the principal workhorse for us for actually simulating molecules. So quantum computers, despite those sort of error thresholds that we're at, and despite not being super effective at running what you might see in a lot of popular science articles like Shor's algorithm, you can still do an enormous amount of useful computation, I would say, today. But with that said, I think that there's a good road ahead. I don't think that the problems in quantum computer science are really scientific. I think they're mostly engineering. I won't scroll back, but in one of those slides I showed all these coax cables. It's of interest, for instance, to not have 200 coax cables going into a machine, and thinking about engineering that away, I think, is actually going to solve most of, or a good deal of fidelity problems. Yep.
Great. Please.
Which interpretation of quantum mechanics informs your intuition?
The question was, which interpretation of quantum mechanics informs my intuitions? So this is maybe not the answer you're looking for, but me not being a physicist, it doesn't really matter to me. When I originally coded, when I was getting used to this stuff and understanding it, I'm like, maybe the multiverse interpretation is a good way to think about this stuff. So I actually wrote an interpreter where every time an operation happened, it simulated the splitting of the universe. And then in each of those universes, every time an operation happened, those themselves split. For me, it hasn't been useful to think about a physical interpretation of quantum mechanics, probably partially because I don't care a lot, but also because I think of this way in which I think about quantum computation that I presented today is much more fruitful in eventually getting things to work and get done.
Okay. Does anyone else have any other questions? I'm sure also Robert will be available a little bit afterwards the lecture if you would like to sort of come and have a personal chat with him. And also some of the other colleagues that Robert mentioned and thanked at the end of his talk, most of those are also have also managed to travel, some quite some distance to be here today, also obviously have a lot of knowledge in this area, and will be hanging around at the end of the lecture. So I think with that, I would like to thank Robert once again, thank everybody for attending. I think it's been a very interesting lecture. Hopefully we've started what will become the annual series of the Marc Grenville-Cleave Memorial Lecture, which each year will be dedicated to some kind of computing topic, be it old or new, in Marc's memory, being his real passions and real interests. And thank you very much for everyone coming tonight. Thank you.
Thank you.